This video explores the topic of Internet of Things and Industrial Internet of Things within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. In this slide, we introduce the basic concepts of the Internet of Things and Industrial Internet of Things. The Internet of Things refers to a network of everyday devices, like smartwatches and home thermostats, connected to the Internet to collect and exchange data. On the industrial side, Industrial Internet of Things uses similar technology, but focuses on machinery, production lines, and factory automation. Both systems rely on devices, sensors, connectivity, cloud platforms, and data analytics to support smart, automated decisions. Here, we compare the Internet of Things and Industrial Internet of Things. Consumer Internet of Things devices are used in homes and wearables, where delays or occasional failures are acceptable. But Industrial Internet of Things operates in industrial environments, where reliability and low latency are crucial, for example in automated assembly lines or power grid control systems. Sensors are the eyes and ears of Internet of Things systems. They capture physical quantities like temperature, gas levels, motion, or humidity. For instance, a DHT22 sensor reads temperature and humidity in smart agriculture, while a PIR sensor detects motion in security systems. These data streams form the basis for real-time monitoring and control. Actuators act based on sensor inputs. For example, if a sensor detects high temperature, an actuator can activate a fan or cooling system. Common actuators include servo motors, solenoid valves, and relays. They are controlled through protocols like PWM or GPIO and are essential for closing the control loop in automation systems. This slide introduces the concept of machine-to-machine, M2M, communication. At its core, M2M refers to the direct exchange of data between devices without any human intervention. It serves as the foundation for automation in both the Internet of Things and the Industrial Internet of Things. Typical devices involved in M2M setups include sensors, actuators, programmable logic controllers, PLCs, and gateways. These components work together to collect, send, and act upon data in real time. M2M communication is widely used across various industries, like smart grids, industrial automation, logistics, smart homes, and even healthcare, because it allows machines to respond instantly to changes in the environment. One simple example is a temperature sensor that detects a temperature rise and sends a signal to a PLC, which then activates a cooling system. This process happens without human input, improving speed, efficiency, and reliability in operations. This slide presents two key communication protocols used in M2M systems, MQTT and COAP. MQTT, or Message Queuing Telemetry Transport, is a lightweight publish/subscribe protocol. It's well suited for situations with limited bandwidth or high latency, which is why it's commonly used in industrial environments and remote Internet of Things systems. COAP, the Constrained Application Protocol, is designed specifically for low-power, resource-constrained devices. It follows a REST-based architecture and supports features like resource discovery. You will often find it used in smart homes, wearables, and other energy-efficient applications. Both protocols are essential for enabling reliable and scalable communication between devices. They ensure that real-time control and automation can function smoothly across various Internet of Things and Industrial Internet of Things systems. On this slide, we introduce several widely used communication protocols In Internet of Things and Industrial Internet of Things systems, Wi-Fi is often used where high bandwidth is needed, but its range and power consumption limit its use in some industrial settings. Zigbee, on the other hand, is optimized for low power, low data rate applications and can form mesh networks. Bluetooth is great for short-range, low-energy needs, such as wearables. For large-scale industrial monitoring, LoRaWAN excels due to its long-range, low-power characteristics. Understanding these protocols helps determine the best fit for each application. This slide helps students understand how protocol choice depends on real-world constraints. For instance, in a smart factory, Zigbee or Wi-Fi might be preferred depending on the environment and device energy profiles. In agriculture, LoRaWAN is often ideal due to its low power and long-range capabilities. For wearables, Bluetooth provides efficient short-range communication. By analyzing these parameters, we can optimize the communication infrastructure for each Internet of Things or Industrial Internet of Things deployment. Wearables are smart electronic devices designed to be worn on the body. They usually include built-in sensors and wireless communication capabilities. Common examples include smartwatches, fitness bands, augmented reality glasses, and even biometric clothing. In the Internet of Things ecosystem, wearables function as data-generating endpoints. They collect a wide range of data, such as biometric, environmental, or motion data, and send it to edge or cloud systems using protocols like Bluetooth, Wi-Fi, Zigbee, or LPWAN. This enables real-time monitoring, automation, and context-aware responses in both consumer and industrial settings. Wearables play a vital role in improving safety and efficiency in industrial environments. For example, they can send real-time alerts if a worker shows signs of fatigue, poor posture, or exposure to harmful gases. Location tracking helps manage access and evacuation in hazardous zones, while smart glasses provide remote assistance and augmented reality-guided workflows. On a broader level, the continuous data from wearables supports automation and smarter decision-making. This data integrates with enterprise and control systems to optimize processes and improve worker well-being. The result is fewer accidents, better situational awareness, and stronger integration with digital twins and industrial systems. In this final slide, we recap the essential points. We started with the distinction between Internet of Things and Industrial Internet of Things, consumer convenience versus industrial precision. Then, we explored how sensors collect data and actuators respond to it, forming the nervous system of these systems. Machine-to-machine communication allows devices to operate autonomously. Choosing the right protocol depends on factors like range and power. Finally, we saw how wearables are revolutionizing worker safety and monitoring in industrial settings. Together, these elements form the foundation of intelligent, connected systems. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.